Friends, so far we have studied the modeling of synchronous generator and steam turbine governors, hydro turbines and hydro turbine governors. We have also studied the modeling of excitation systems. Now, this completes the modeling on the generator side, right. We have also assumed actually that for power system stability studies, the transmission line network is modeled under steady state conditions. Now, we have to model one very important component, that is the loads in the system. The modeling of loads has important influence on the stability of the system. Further, the modeling of load is the most complicated process. The reason being that whenever we try to model the load in the power system stability studies, right, we identified some load buses, and at that load bus we have variety of loads which are supplied. The loads supplied are the lighting loads, heating loads, cooling loads, motor loads, furnaces and so on, right, and all these loads have different characteristics. Now, with the classical stability studies, we represent load at a bus by constant impedance load. However, the studies have shown actually that this representation may give some erroneous results, and therefore, there has been over the years efforts being put to develop the models of the system. Now, the problem is because the loads are of different variety, and this composition of load at a particular bus is also not fixed. It varies from time to time, is a function of time. It also is a function of season, weather conditions and so on. And therefore, whenever we develop the load models, we do lot of simplifications, right. Now, today in our study, we will look into the modeling aspect of the loads for power system stability studies. Now, traditionally for the purpose of modeling or for the purpose of representing loads in stability studies, the load models are classified into two categories. One is called static load models, another is dynamic load models. The dynamic load models are normally required or essentially required for long term stability study, voltage stability, and when you want to study the interior oscillations, right. Now, today we will briefly discuss how the loads are represented as static loads and dynamic loads. When I talk about the dynamic loads, we have a number of loads which are thermostatically controlled loads. When I say thermostatically controlled loads, for example, most of the heating loads are thermostatically controlled loads, right. The temperature is controlled and the thermostat is on and off. Similarly, there are number of examples like refrigerators, coolers, right, and so on. Then we have another very big component in our load, that is the discharge lighting loads, where you have the fluorescent tubes, we have the sodium vapor lamps and mercury vapor lamps. Now, they are all under the category of discharge lighting loads. The third most important component in the dynamic loads is the induction motor loads. In any system, about 60% load, 60 to 70% load is due to motors, and the modeling of these motors is very important, and lot of attention has been given to modeling these large size induction motors for stability studies, right. Because in power plants or actually in some big industries, we have large size induction motors, and their characteristic affect the system stability as a whole, right. Now, first we will address the modeling of static loads. Now, when I talk about the modeling of static loads, right, then we represent the load at any time a function of voltage magnitude and frequency, right. Now, here the load will be expressed in terms of voltage and frequency using algebraic expressions, because it is not a dynamic load, right. Therefore, the equations which are used to represent static loads will be algebraic equations, okay. And since these loads are function of the magnitude of the system voltage and system frequency, we will represent these loads as using algebraic expressions in terms of voltage magnitude and system frequency. Now, for representing these load models, we will consider the real power and reactive power components of the load separately, because the behavior of the reactive power consumed by a load and the real power consumed by the load following variation in voltage and frequency, they are somewhat different. Now, let us see what different load models have been used in the literature. A simplest load model considering the voltage variation is shown in this form, that is, the P is the real power consumed by a load at any voltage V equal to P O into V bar to the power A. A is an index, A is some index, right. Therefore, we can say where this V bar is defined as V divided by V O, where V O is the nominal voltage at which the power consumed is P O, right. And therefore, this V bar is a fraction of the actual voltage and the nominal voltage, or you can say that this V bar is a per unit voltage expressed in terms of V O. Okay. Therefore, P can be expressed as the nominal value of the real power consumed P O multiplied by this V bar to the power A. Then similarly, the reactive power Q is dependent as Q O into V to the power B, V bar to the power B. A and B are the two different indices. Now, here suppose if I take A and B equal to 0, both let us say that these coefficients are 0. What does it mean? P equal to P O. It means the load is independent of voltage, right. Now, suppose I take A equal to 1 and B equal to 1. If I take these coefficients A equal to 1, B equal to 1, what does it represent? Yes. Therefore, here the meaning is that the load draws constant current, right, and therefore, the power is proportional to the voltage. Power P and Q which are consumed, they are proportional to the voltage. Now, if I take these indices A and B, indices A and B equal to 2, that shows that the power consumed is proportional to V square, and that is the characteristic of a constant impedance load. For example, in our tangent stability studies, classical tangent stability studies which we discussed, we were representing the loads by constant impedance. At that time the index becomes 2. Therefore, we have, by putting the different values of A and B, we can have different representation of loads, whether the load is a constant power load, constant current load or constant impedance load. Now, in practice the loads different loads behave in a different way, different devices. I just take the example of say incandescent lamp. Okay. Now, this lamp does not consume reactive power, right, and the power consumed by this will be proportional to V square, although it is not very linear, but it is for a small variation it is proportional to V square, and therefore, this load will behave like a constant impedance load, while there are other loads, they have different characteristics. And in at any bus we have different devices, and therefore, we may divide this load into 3 different categories, like say constant power load, constant impedance load and constant current loads, right. Now, if we in case we want to represent a composite load, then these coefficients A and B will be different. For example, for a composite load, this index A varies from 0.5 to 1.8. Similarly, B has a wide variation, that is 1.5 to 6 for composite loads. Again, it depends upon what is the composition. Now, here the loads, right, which we represent by static loads, they generally have very high response, in the sense that when the voltage and frequency changes, right, the power consumed also changes practically instantaneously. There is no time delay, right, and therefore, at any instant of time they can be represented as static loads, and the variation can be represented using algebraic equations. Any composite load can now be represented as in terms of 3 components. We normally call this as ZIP representation. Z means constant impedance, I stands for constant current and P for constant power. Therefore, you can have a load representation by this equation P equal to P naught multiplied by P 1 into V square, V bar square, plus P 2 into V bar plus P 3. Now, this P 1, P 2 and P 3, these are the fractions of the load which represent the constant impedance, constant current and constant power fractions. Okay. Suppose I take P 1 equal to 0.5, P 2 equal to say 0.3 and P 3 equal to 0.2. That means, the 20% load is a constant power load, 30% load is a constant current load and 50% load is a constant impedance load. Similarly, reactive power, that is reactive power Q can be represented as Q naught into V 1, Q 1 into V bar square plus Q 2 into V bar plus Q 3 plus Q 3, which is multiplied by Q naught. Okay. The basic problem comes is actually difficult to know these fractions P 1, P 2 and P 3. The next important aspect of static load modeling is the frequency dependency of loads. This is a very important component or very important aspect of load modeling, that is the loads depend on the system frequency. in most of the cases the real power consumed by the load increases when frequency increases, and real power consumed by the load decreases when frequency decreases. And in our Indian power system, where we do not have enough generation, right, the load depending upon frequency, right, that is these loads decide actually the system frequency, that is generations are practically constant. When you put additional load, frequency drops, right, and therefore at a lower frequency we are in a position to meet the additional load which comes. Although the total power which is fed is same, right, but whenever additional load comes, what happens? Suppose your system is operating at a certain frequency, and let us put that I switch on some additional load of say 1 megawatt. This additional load will be met, but from where it comes? Because the answer is that under steady state conditions, this additional load is met by one component is the release of the existing load plus the increase in the generation. While in dynamic condition we have all the 3 points, the release by the existing load, increase in generation and change in kinetic energy. But the moment you attain the steady state condition, right, this change in kinetic energy component becomes 0 because you attain the constant speed again, right. This is the way the system operates, right, when you are trying to match the generation with the load, okay. Because whenever additional load comes, the first thing which happens is the frequency drops, okay, and initially this additional load is made by kinetic energy, mainly change in kinetic energy. Then the regulators the governors will come into action, will increase the generation, and when the frequency drops, the existing load will start consuming less power, they release some power, right. Therefore, these are the 3 components, and therefore, here we are trying to address this thing that if the frequency changes, how the real power and reactive power consumed vary. Now, this equation which is shown here shows the variation of real power consumed by the load with the variation of magnitude of voltage as well as frequency. That is, if I consider this general equation to represent the real power variation with magnitude of voltage, and I multiply this expression by this term 1 plus Kpf into delta f, right. Now, this term Kpf is this coefficient is an important, it is the characteristic of the system, okay. Similarly, the reactive power consumed can be represented as Qo V bar to the power B into 1 plus Kqf into delta f, okay, in the sense that both P and Q are now represented as function of system voltage magnitude and frequency deviation, okay. Now, suppose if we represent the load by this expression, that is ZIP representation, okay. So, you can represent P equal to P naught into P1 V bar square plus P2 V bar plus P3, then this whole thing is multiplied by this fraction, this factor is 1 plus Kpf into delta f, okay. Similarly, Q can be represented as Q naught into Q1 V bar square plus Q2 into V bar plus Q3 into this. Therefore, this becomes a very general representation of a load which now accounts for change in magnitude of the voltage and also change in frequency, that is frequency deviation. Now, here one has to understand what are the values of this coefficient Kpf and Kqf. Now, so far the real power consumed is concerned, right. As the frequency increases, the real power consumed increases, and therefore, this Kpf will always be positive. Kpf is always positive, and this delta f is expressed as, delta f is defined as the actual frequency of the system minus the nominal frequency, f minus f. The delta f is positive when the actual system frequency is more than the nominal frequency, right, and therefore, this coefficient Kpf is always positive, but it varies. It is different for different loads. It is different for different loads. There are some loads where the power consumed does not depend upon frequency. Lighting load flow, particularly this you know, these powers, particularly the fluorescent tubes or you know, all sodium vapor lamp or mercury lamp, they do depend upon frequency, but particularly incandescent lamps. Suppose I have actually a room heater, a road type room heater, then it will not depend upon frequency. So far magnitude of voltage is same, right. But since the loads are composite loads, and therefore, this is a very important coefficient to be known, and it is difficult. Again, estimating this coefficient is a very difficult task actually for power system engineering. Those who are taking the course on power system control and instrumentation, we use the term load frequency constant D, a parameter load frequency constant D. This D is same as this term Kpf, which I call it. Now, what about Kqf? Whether this is also positive all through, or whether it is always negative, or what should be the value of this Kpf?
Maybe positive or maybe negative, depending on leading power factor or lagging power.
The response of the audience here is that it may be positive or negative, but answer is not correct.
Negative.
It is always negative. Always negative. We can easily understand why it is negative. The typical values of Kpf is from 0 to 3, and Kqf is in the range of -2 to 0. -2 to 0. These are the typical values of these coefficients. This is a wide range, depends upon the type of load. In the literature, there is one more way of representing this representing the static loads, right. That is, the static load model can be represented as P equal to P naught multiplied by P ZIP plus P EX1 plus P EX2, where P ZIP is represented by this expression P1 V bar square plus P2 V bar plus P3. That is what we have already seen. Then P EX1, that is exponential component, is represented as P4 V bar to the power A1 multiplied by this term 1 plus Kpf1 delta f. P Ex2 as P5 V bar A2 into 1 plus Kpf2 delta f. In fact, the load models which have been used actually and used in analyzing the stability of the system, right, the results which are obtained and the actual thing which happens in the ground, right. Suppose actually for a given operating condition, right, my stability study shows that I have this much stability margin, while in practice you will not achieve that much, and that has been the concern actually for the power system engineers, because generally we do most of these studies offline using the system models, okay. And when you try to see what happens on the field, right, for the similar operating conditions, right, sometimes it is seen actually that the results obtained by offline studies and what happens on the ground, there is a lot of variation, and that is why actually all through the efforts are being made to have more detailed model of the system. Because when I talk about the stability studies, then the crux of the whole problem is the detailed model of the system, right. As we have seen actually that we have to model all these subsystems in detail: synchronous generator, excitation system, governing system, turbine system, and even we have not gone to the boiler models. The boiler models are also required, transmission line models are required, load models are required, right. And in case there is a big approximation or error in this modeling, the results are going to be different or erroneous, and that is why a lot of efforts are being made to develop better and better model and to estimate these parameters by doing some experiments in the field, right. This is because suppose I take this model, then it has how many coefficients to be estimated. I require this coefficient KPF1 and KPF2. It means I have two different coefficients which determine the frequency dependency of loads, right. Similarly, this P1, P2, P3, P4, P5, right, and these are to be estimated actually for a particular load bus, and this is quite a involved task. Now we will discuss the dynamic load models. This is all about the static load models, and justification of static load models is that whenever the magnitude of frequency and voltage changes, right, the new value of power consumed changes quickly. In the sense the response time is practically low, and therefore we can represent these loads by static models. But there are so many loads actually which need to be modeled in a dynamic way, and particularly this dynamic modeling or load modeling is needed when we are doing inter-area oscillation studies. That is, we want to study the behavior of the system when it is subjected to inter-area oscillations, the long term phenomena. Similarly, we are studying the long term or mid term stability or voltage stability of the system, right. During that period, the load models or dynamic load models are also required. Now here the aspects to be considered will be the discharge lamps. I have talked about the discharge lamps, the fluorescent lamps, the sodium vapor lamps, and the incandescent lamp is not a discharge lamp, mercury arc or mercury vapor lamps. Okay. In these lamps there is a very important thing actually, at the moment the voltage is around 0.7 to 0.8 per unit, these lamps extinguish, and when the voltage recovers within 1 or 2 seconds they are restored back. Understand, this is a very interesting thing, that in a power system when we are doing the stability studies under disturbance condition, the voltage at various buses vary, and in case the voltage at a particular point at a particular bus becomes less than about 70 to 80%, then these discharge lamps extinguish, and when the voltage is restored back, right, then they are restored back after 1 or 2 seconds, because when I switch on a fluorescent lamp, it takes 1 or 2 seconds to be put on, right. This is one of the important characteristics to be modeled. Then there are many devices which have the overcurrent and thermal relays. These are also required to be modeled. Then the thermostatic control of loads, particularly these thermostatic control loads are mostly heating and cooling loads, air heating, air cooling, refrigerators, and some other devices which you can look into it. Then another very interesting thing which we have to understand is that in the distribution system we have underload tap changing systems, ULTCs. In distribution systems we have some voltage regulators which regulate the system voltage. ULTCs are also for regulating the voltage. And then we also have actually in distribution system the switch capacitors, voltage control capacitors, right. Now, whenever actually the system voltage dips or becomes low, then these ULTCs will try to operate and regulate the voltage. You know, that is, suppose actually at a particular time the voltage has dipped, right. Then the on-load tap changers or underload tap changers, right, they will operate to increase the voltage, but the response time is quite high. The voltage is low. After about 1 minute they start operating, and their operation is completed in about 1 or 2 minutes time. They are slow devices. Then there are many voltage control capacitors, right. If the voltage is high, the capacitors will be switched off, and when the voltage is low, capacitors are switched on, right. And further, the reactive power which is consumed by these capacitors also depends upon the system voltage, and therefore these are all the aspects which have to be considered while doing the modeling. In fact, the one stability program which has been developed by EPRI, we call Electric Power Research Institute USA, right. They have modeled the thermostatically controlled loads and also the induction motor loads in their system. They call it, the program is called load scene. There are many utility companies, they have purchased those programs. Although question is that whether we are fully utilizing those software packages for operating our system, that is a different issue, but detailed stability programs accounting for the load models are available globally. Now, here I would like to discuss actually the thermostatically controlled loads. Let us take the example where actually the load is to heat a particular space heating, right, and the differential equation which governs the heating process or temperature control is written by this equation, that is K times d tau h by dt equal to pH minus Pn. This is a very important equation, because once I say it is a dynamic model, then these derivative terms will come. We will have to have differential equations to represent certain devices. That is constant coefficient K d by dt of tau h pH minus PL. Here this tau h is the temperature of the heated area. Tau h is the temperature of the heated area which we want to regulate, want to control. How do we control this? By increasing or decreasing the heat generated by the heating device. Now, here on this right hand side we have the two terms pH and PL. pH stands for the power from the heater. This pH can be represented as a function of constant KH, G is the conductance of the system, and V square. Now, since actually we are trying to study the stability effect of these devices on stability, because the power consumed here is function of voltage V square, right. Therefore, the power from the heater is shown as constant into conductance into V square. Then PL stands for the heat loss by escape to ambient area, atmosphere. This is the heat dissipation, which can be represented by a constant K into tau H minus tau A, where tau A is the temperature of the ambient, or we can say ambient temperature. G is the load coefficient. Okay. Now, this equation has been put in a form where I can realize the transfer function relating the actual temperature of the system and actual conductance of the system. Now, to do this thing, what we do is that in this equation we substitute for pH and PL these quantities. Now, when you make the substitution, this K times tau H by dt. For pH I am putting KH G V square, and for PL we are putting Ka into tau H minus tau A. Okay. Then you simplify this equation and arrange the terms. You will get the term is d tau H by dt equal to K1 by T1 G V square plus 1 by T1 tau A minus 1 upon T1 tau H. Where these quantities are defined like this, T1 is equal to K by Ka and K1 is defined as Kh by Ka. They are just the definitions. Okay. Now, this equation, if you take the Laplace transform of this equation, you can put in the form of a transfer function. I will just show you how it is put in the form of a transfer function. In any system, we want to regulate the temperature, right? Then we start with the reference temperature, let us call it tau reference, and we want to know what is the actual temperature at any time t of the space. Okay. Now, this equation, that is, see this equation, this differential equation relates actually the time at any time t with other parameters of the system. This is a simple differential equation. Now, this can be put in this form. Now, if you see here actually in this differential equation, then we can represent this differential equation by this form, that is G is the system conductance. You multiply this G by V square, GV square multiplied by K1. Okay. To this you add this ambient temperature tau A. Okay. Then when it passes through this transfer function 1 upon 1 plus SIM T1, you will get a term tau H. Now, in practice what is done is that this error, this is the error signal, we call it tau error, right. This will be put into a controller to regulate the conductance of the system. Generally we use a PI controller. If you use a PI controller, you can have the proportional gain setting Kp here, and you put integral control, I am just putting on this side, is it can be, it is Ki divided by some time constant Tc s, and here we have to put the upper maximum limit G max. You can add these two outputs. Again there will be a maximum limit which has to be put G max, and this conductance is the one which. Now this becomes a simple closed loop control system which we can show here to regulate the temperature of a space which is to be heated. Now here tau h is the state variable, the only simple, and this is the PI controller which we have shown. Now depending upon this error, it is going to increase the or decrease the conductance, right. The more the conductance, right, the more is the heat which is going to be generated, right. But since you have using this integral also, so that we want actually that the maximum conductance should be limited. Therefore maximum limit either it may be touched by the integral integrator or by the sum, because here it is plus. Okay. Therefore this is one way of, you can say, representing thermostatically controlled loads. Now under steady state conditions, the tau reference equal to tau h, right. Now if you make this substitution in this equation, in this differential equation, put the derivative term to 0, when I make derivative term equal to 0, right, then we can write down the tau reference equal to K1 times V naught square GO plus tau A. That is the reference temperature setting which is required to attain the required value of tau h, where the constant K1 is equal to tau reference minus tau A divided by VO square GO. Okay. Now with this, I have just to have briefly introduced actually that how a dynamically controlled or thermostatically controlled load can be represented. These differential equations are to be written along with the system differential equations. So far actually the discharge lengths are concerned, their characteristics can also be shown as function of voltage, but these characteristics are quite non-linear in nature. I show on this axis P and Q consumed by the discharge lengths, and on this x-axis we put voltage V. Okay. Now let us first see the power P consumed by a discharge length. At a certain voltage, up to certain voltage, say V1, the discharge length will be off, right. Therefore no power is consumed by discharge length. When the voltage becomes V1, suddenly these devices are switched on, and when the voltage increases beyond this, the power consumed, that is at time when the voltage is V1, the power consumed suddenly jumps from 0 value to this value. Then as the voltage further increases, the power consumed may vary linearly and by another segment. In fact, actually you can do this nonlinear characteristic and represent by a piecewise linearized model. That is, you can put at this voltage V1, from V1 to V2 it can be represented as some Kp1 into V, and here it can be represented as Kp2 into. Okay. While this so far the reactive power is consumed, the reactive power variation is very non-linear in nature. Therefore, reactive power variation for these devices can be shown. This type of curve, we can call this as Q, which is equal to Q naught, the value at this particular point, multiplied by V to the power some coefficient k, a very non-linear type of variation. And therefore, since this system voltage is varying, when you want to model these devices, this type of model is to be shown, that in case the voltage is less than V1, they are off. When it is more than V1 to V2, P and Q have to be shown by this. That is, in the model you have to have that facility where you represent the loads that are present as a function of voltage. Okay. The next important component for modeling is the induction motor load. Now, induction motor load or modeling of induction motor has attracted the attention of many researchers and many practicing engineers in the past, because about 70% of the system load is induction motor load. Now, for developing this dynamic model for the induction motor, the approach is similar to what we do for a synchronous motor, and we represent the model using DQ transformation. DQ transformation. I will not go into details about all these transformations, but here we have one simple advantage actually. For so far this induction motor is concerned, the rotor of the induction motor is a cylindrical one, right? And therefore, the variation in mutual inductances and self inductances, right, are different as compared to that of a synchronous motor. Let us just see. So far the stator windings are concerned, they will not see any difference in the reluctance of the magnetic circuit as the position of the rotor changes. Rotor is cylindrical, therefore, whichever is the position of the rotor, right, the stator windings will not see any difference in the reluctance, and therefore, the self inductance of the stator winding, the mutual inductance between the stator windings are not function of angle. This is the advantage. Second point is that the mutual inductance between the stator and rotor windings vary because the axis of the rotor and stator windings are having different orientations. When the axis of the rotor and stator windings are aligned, they will have maximum mutual inductance. When they are in quadrature, it will be zero mutual inductance. That is the only variation. And here the stator voltages are written in terms of the D and Q axis components, just as we do in the case of synchronous machine. But here we also require the transformation for rotor quantities. This is another difference. Further, for studies, the transformer voltages in the stator circuit will be neglected. The stator circuit, for example, for stability studies in the synchronous machine, we have ignored the transformer voltages in the stator voltage equations. Similarly, here also we ignore it. However, actually the transformer voltage in the rotor circuit will not be ignored. While this rotor circuit is concerned, the rotor is a closed circuit, therefore D and Q axis voltages in the rotor circuit are 0. That is VDR and VQ are set equal to. Okay, these are the simple equations which can be easily derived, and they are available in the standard literature. The stator of the synchronous generator can be simply represented by a model of this form. This is a simple model which one can arrive at for the stator equations, because the stator equations we have not considered the transformer voltages, right. Therefore, this is a algebraic equation. We can represent this voltage Vs bar as Rs plus J times Xs bar into Is plus V prime. This is an important voltage component. Okay. When you represent these voltages in terms of D and Q axis components, we can write down Vs equal to Vds plus J times Q Vdqs, V prime equal to Vd prime plus J times Vq prime. Then here the two components of this voltage V prime has these two components Vd prime and Vq prime, right. These voltages are obtained from these two differential equations, that is P Vd prime is given by this equation and P Vq prime is given by this equation. That is two differential equations. In fact, basically these equations represent the rotor dynamics. Rotor dynamics, as I have told you that we do not neglect the rotor dynamics here. If you neglect rotor dynamics, then this model also becomes a static model. Okay. Now here there is a term, very important term, TO prime. This is the transient open circuit time constant. Transient open circuit time constant. And this time constant, this TO prime, characterizes the decay of the rotor transients when the rotor is open circuited. I am sorry, there is mistake here. There is when the stator is open circuited. When the stator is open circuited. The differential equation for the induction motor, just like actually we have a swing equation for synchronous jetter. Similarly, we have a swing equation for induction motor is d by dt of P omega r bar equal to 1 upon 2h Te minus Tm. Now here electrical power, right, is the input and mechanical power is the output. Therefore, Te minus Tm is the accelerating torque, right. Therefore, this is the swing equation for the induction motor, and this electrical torque is obtained by this equation T equal to Vd prime Ids plus Vq prime Iqs. Further, the load torque, because Tm is the load torque, this Tm is the load torque, right. This load torque also depends upon the speed, and therefore the equation which is used to represent the load torque Tm is To omega r to the power m omega r bar. Here omega r bar means it is actually the speed of the rotor expressed in terms of or you can say synchronous speed of the machine. Okay, that is, you can say it is a per unit speed. Omega r bar is a per unit speed. Another expression for torque may be Tm equal to To into A times omega r square plus B times omega r plus C. Now let me conclude today's presentation. Today we have discussed the static and dynamic models for the loads which are required to be modeled in the stability studies of the power system. We have modeled the various types of loads, and the loads which we consider are actually the static loads and the dynamic loads. In dynamic loads particularly we have determined the dynamic model for the induction motor. Thank you.